One of the most puzzling phenomena are black holes extraordinary, events in the universe that are still the subject of intense analysis and enchantment for astronomers and theoretical scientists alike. These astronomical objects are characterized by their immense gravitational strength and the complete absence of emitted light, indicating a threshold beyond which established physical science principles cease to function. Originally hypothesized in 1916 by Albert Einstein as a result of his general theory of relativity, black holes remained purely hypothetical until modern technology made it possible to observe them in the 21st century. A pivotal moment emerged in the 1960s, when researchers examining the Cygnus constellation inadvertently identified an unusual star with a brilliant blue body. Releasing intense X-ray radiation, this star locked in orbit with an unseen partner, resisted conventional explanations until it was found to be entangled in the gravitational pull of a huge black hole now known as Cygnus X1. The detection of Cygnus X1 offered tangible proof of black holes' existence and initiated a transformational period of research into these cosmic mysteries. Located about 6,000 light-years away from our planet, Cygnus X1 possesses remarkable features. It is extraordinarily compact and produces a gravitational influence so strong that even photons cannot escape, a central feature that led to the name black hole, successfully conveying the essence of these enigmatic structures. Subsequent investigations have identified a diverse collection of dispersed black holes across the universe. Projections indicate that the Milky Way galaxy alone could contain more than 100 million. Despite their properties complicating direct observation, astronomers have recognized numerous possible examples, ranging from stellar mass black holes originating from the collapsed cores of enormous stars to supermassive black holes residing in galactic centers. The gravitational pull of black holes affects more than just nearby space. It influences the development of universal structures and the fate of adjacent matter that drifts too close to a black hole's event horizon. A final boundary in the area is gradually drawn in by unyielding gravitational power. Within this region, it experiences extreme gravitational stretching and is ultimately absorbed by the singularity at the center. This dramatic process, called spaghettification, results from a black hole's immense gravitational dominance. An object nears the event horizon. It's the difference in gravitational pulling against. Structure becomes so extreme that it is elongated and deformed into a thin strand resembling spaghetti. The gravitational forces surpass the unified bonds that hold the object together, disassembling it into a stream of particles that, in the end, integrate with the singularity. Though black holes provide a remarkable opportunity for examining the extremes of physics, they remain cloaked in mystery. Nature persists in its attempt to comprehend the core aspects of spacetime and gravitational mechanics. Amid the vast expanse of the cosmos, black holes act as insidious guardians, inviting humankind to delve deeper into the uncharted and broaden the boundaries of comprehension. Despite the immense distance of the nearest known black holes, to be around 1,500 light-years away, questions and apprehensions regarding their possible effects persist. In 2021, scientists made a significant breakthrough by obtaining the first definitive image of a particular black hole, the one at the center of galaxy M87. This extraordinary feat delivered pivotal knowledge about black holes and their elusive form. The captured imagery showed that black holes consist of intricate layers, confronting the long-standing notion of them being isolated voids of absolute emptiness. Through detailed study and image compilation, researchers discerned 3 distinct layers within a black hole. The outermost is the event horizon, a vital boundary indicating the limit beyond which return is impossible. Once something crosses this threshold, gravitational acceleration becomes unstoppable, sealing its plunge into the depths of the black hole, moving inward. The second layer is the photon-sphere zone, where light orbits the black hole endlessly. Any photons entering this area are dominated by gravitational influence and remain forever trapped within the black hole's grasp. At the very center exists the singularity, the third and final zone, where physical laws disintegrate. The familiar principles that govern space and matter collapse, introducing scientists to a realm of vast ambiguity and theoretical conjecture. The inherent intricacy and diversity of black holes pose major hurdles for scientific interpretation, even though many exhibit a common three-layer model. Each black hole has distinct actions and properties that evade straightforward classification. Consequently, traditional scientific methodologies often fall short when exploring these immense cosmic phenomena, requiring new and creative methods to bring their truths to light. Since direct TAL analysis is not feasible due to overwhelming gravitational constraints, indirect monitoring continues to be the primary method for examining black holes. Any mission attempting to deploy instruments into a black hole would face inevitable destruction within its most extreme gravitational environment. Still, researchers maintain their pursuit of understanding these astronomical titans. Numerous hypotheses from stellar collapse to dynamic cosmic evolution provide captivating insights into their origins. Observations by NASA of the central region of M87 uncovered convincing signs of a supermassive black hole influencing vast regions of space. Despite numerous challenges, the desire for discovery advances, fueled by the inherent human drive to investigate and explain. Although black holes may defy basic understanding, the enduring commitment to scientific discovery holds promise for revealing the darkest secrets of the universe. Roy Kerr's revolutionary findings in 1963 introduced a game-changing view of black holes by proposing a model of rotating black holes that challenged accepted doctrines. A cornerstone of Kerr's theory was the ergosphere surrounding region where opposing forces neutralized total gravitational collapse, preventing matter from plunging further inside. In this peculiar area, remarkable deviations from standard physics point to the deep puzzles buried within black holes. However, perhaps the most captivating outcome of Kerr's hypothesis was the suggestion of an Einstein-Rosen bridge, or a wormhole, a speculative construct that could link distant regions of space or even parallel realities. The wormhole concept emerges from a sophisticated relationship exists between the real world and the principles defined by general relativity. In this vision, reality is woven into a tapestry with 4 dimensions referred to as space-time, with mass warp distortions causing gravitational effects we observe. Wormholes are essentially shortcuts through this vast fabric, potentially joining 2 distinct places in space and facilitating rapid transit across the cosmos. Still, the reliability and usability of their structure remain contentious among physicists. While wormholes open up thrilling possibilities for interstellar travel and temporal experimentation, significant obstacles and theoretically inconsistent behavior dampen these hopes and visions. Their fragile nature, along with challenges posed by the theory of quantum radiation, casts doubt on their functionality as transport mechanisms. Furthermore, general relativity sets hard limits on movement speeds through spacetime, implying that even if wormholes were stable, they might prohibit travel faster than light, a hallmark of science fiction. Despite this, wormholes continued to inspire scientific inquiry. The notion, named after their foundational theorists, embodies the thrilling idea of universal passageways and alternate dimensions, igniting humanity's imagination about the broader cosmos and its infinite potential. The ambition to forge a single, unified explanation that bridges the gap between gravity and quantum mechanics has led scientists toward a theory of everything, a total model that encompasses all elementary forces and particles. The renowned physicist heading this mission is a pioneer of M-theory, whose research has advanced superstring theory. This theory marks a profound shift from conventional paradigms by proposing that the smallest units of matter are not elementary particles but tiny vibrating strings similar to those on musical instruments. These strings vibrate at unique frequencies that produce all known matter and forces. In this view, the universe resembles a grand composition, with each particle symbolizing a specific tone of these superstrings. This theory may also illuminate some of the most puzzling features of black holes, wormholes, and other exotic elements within Einstein's gravity equations. The movement of strings through space-time contributes to the emergence of singularities and topological oddities. Despite its beauty, superstring theory is extremely complicated and requires the existence of additional dimensions beyond the familiar three-spatial and one-time dimension. These hidden dimensions, not directly observable, challenge human perception. Analogies such as fish living on a two-dimensional surface help explain how beings in a limited dimension might be unaware of higher spatial planes. These hidden dimensions are believed to be compactified or curled up, making them undetectable in daily life. Yet, they significantly influence physical phenomena. Even though their exact nature remains undetermined, their theoretical presence offers valuable explanations for the universe's strange behaviors. Additionally, the mathematics behind superstring theory has sparked a revival in theoretical physics, demonstrating connections between abstract math and tangible reality. Indeed, the drive to find a unified theory of everything has unified various scientific fields, highlighting the deep relationship between natural numbers and physical laws. However, superstring theory still awaits experimental support, as its predictions are hard to test, especially given the invisibility of higher dimensions. As a result, the daring vision of superstring theory continues to captivate students and dreamers, urging humankind to pursue intellectual growth and a deeper comprehension of the cosmos. As we move through contemporary physics, guided by this luminous theory, we stand on the edge of deeper knowledge and consciousness. Solving the quantum puzzle of black holes has long baffled researchers and remains one of the greatest challenges. In physics, despite countless attempts to resolve this conundrum, a complete answer has proven elusive. Edward Witten from Princeton's Institute for Advanced Study, it's famously called superstring theory 21st century physics that arrived by accident in the 20th century. Yet recent events have rekindled hope. Independently, multiple teams have unveiled major progress, indicating that string theory may indeed provide a comprehensive solution. Though currently limited to simplified models in 2 dimensions, rather than the typical 10-dimensional structure suggested by string theory. Although this marks meaningful advancement, a full resolution is still pending. As the intricacies of the issue present significant challenges, pursuing a unified theory requires us to investigate the outermost regions of the universe, where the boundary between fact and theory blurs. The profound study of black holes holds deep importance for our understanding of the universe. It challenges core beliefs about reality and encourages philosophical thought. The interaction between black holes and additional astronomical phenomena like gamma-ray bursts and neutron stars unveils the delicate mechanisms shaping the structure of the cosmos. These celestial collisions and energetic displays are not merely random. They serve as insightful markers of cosmic behavior, showing how gravity, matter, and energy interact on scales far beyond human experience. Black holes, once thought to be theoretical oddities, now play a central role in explaining the dynamics of galaxies, star formation, and even the evolution of the universe itself. As scientific instruments grow more advanced, from gravitational wave detectors to space-based telescopes, our ability to observe and investigate these enigmatic objects improves. Discoveries such as the observation of gravitational waves ripples in space-time caused by black hole mergers have validated long-standing predictions and introduced a new horizon for astrophysical exploration. At the intersection of observation and theory lies the continued attempt to merge Einstein's general relativity with quantum mechanics, a challenge that black holes uniquely embody. These cosmic singularities present conditions where both sets of rules must apply, yet currently conflict, forcing scientists to rethink the foundations of both disciplines. Like wormholes and black holes, the space-time fabric they manipulate may, in the future, provide the key to gaining access to a more comprehensive model of reality, one that seamlessly includes quantum field theory and gravity. Until then, remain both puzzles and promises, prompting continual inquiry and arousing the imagination of a new generation. From Einstein to Hawking, from string theorists to observational astronomers, the story of black holes reflects the ever-evolving quest to understand our place in the universe. With every equation, simulation, and image captured, we come closer to unraveling not just the secrets of these cosmic powerhouses, but also the fundamental character of existence itself.